Chapter 3 is about garbage collection, the system that automatically reclaims memory your program no longer uses. In languages like C and C++, you manually allocate and free memory. That means you can get dangling pointer bugs accessing memory you already freed, or double free bugs trying to free the same memory twice. You can also get memory leaks by forgetting to free memory at all, or buffer overflows by writing past the end of an allocated region. Node.js uses V8, and V8 manages memory automatically. This removes the most catastrophic bugs, but it introduces a new concern: performance. Garbage collection is not free. In V8, every new variable you create allocates a little memory and inches you closer to the next GC cycle. Every GC cycle pauses JavaScript execution. This is called stop the world, while V8 figures out what's still alive. V8 does expose a GC function if you launch Node with the expose GC flag, and you can tune GC behavior with V8 options. But there's no way to block GC entirely. What you can do is make GC cycles run more frequently but with a smaller footprint. The GC cost is proportional to the number of referencing objects. If you call GC, after substantially reducing your referenced objects, you keep the application lean and reduce the GC penalty for the next cycle. The most important mental model here: think of memory as a graph. Objects are nodes. References between objects are edges. Leaf nodes hold raw data numbers, strings. Non-leaf nodes hold references to other nodes. GC's job is to find nodes with no path from the root, no reference chain leading back to active code, and reclaim them. To work effectively with V8's memory tooling, you need to understand three key concepts: shallow size, retained size, and distance. The shallow size is the memory used by the object itself to store its immediate value. For most objects this is tiny, only strings and arrays can have a meaningful shallow size. The retained size is the size that would be freed if the object were deleted. This includes the object plus all the objects it references that would also become unreachable. An object's retained size is always at least its shallow size, but often much larger. Think of it this way: if you have a node in a graph that references a cluster of other nodes, and all those other nodes are only reachable through this one node, then deleting this node frees all of them. Their combined size is the retained size. Distance is the smallest graph distance from a root node to a given node. A root node is a node from which references start. It's where the graph originates, and it has no incoming edges. In V8 Inspector or Chrome Developer Tools, these are the columns you'll see in the Profiles tab when you take a heap snapshot. Sorting by retained size will immediately surface the objects that are consuming the most effective memory. Sorting by object count helps you find constructors that are being instantiated far more often than expected. Understanding the graph model also explains why nulling a reference doesn't always free an object. If another part of your code, perhaps a function you passed your object to, or an event listener, is still holding a reference, the object stays alive. The GC only sweeps what is truly unreachable from the root. A memory leak is a continuous loss of available memory. It happens when a program repeatedly fails to release memory it's no longer using. In Node.js, memory leaks are usually not the GC's fault, they're caused by object destruction not taking place when it should. And in an event-driven architecture, this is surprisingly easy to get wrong. V8 divides the object heap into two main zones: new space and old space. New space is small and fast, it's where newly created objects live. Objects that survive one or two GC cycles get promoted to old space. Old space can grow very large, from a couple of megabytes to a gigabyte. If your application is leaking memory, objects keep accumulating in old space and the GC cycle for that space, the major cycle, gets longer and more expensive. At some point the application stalls for a second, then several seconds. If you're running at the default 1 GB V8 memory limit and you're not monitoring GC behavior, you'll probably only notice the leaks when your application starts stalling and then stops entirely because it hit the limit. Most objects have one of two lifetimes: very long, like the main server object that exists for the life of the program, or very short, serving a specific request and then being released. GC is optimized for this pattern. Short-lived objects get collected efficiently in the new space miner cycle. Long-lived objects settle into old space and stay there legitimately. Memory leaks happen when medium-lived objects accumulate, objects your code has logically finished with, but which remain referenced somewhere you forgot to clean up.